Now here's another example. I have a 2 degrees of freedom system here. I have two masses connected by a set of springs and dampers, and the freedom here are x1 and x2, and let's derive the equations of motion. And I expect two equations of motion in this case, not because I have two bodies, but because I have 2 degrees of freedom. It's not the number of bodies, it's the number of degrees of freedom. Using Newtonian approach first, I'll have to draw a free body diagram for each one of the two masses here. So I will have one free body diagram for M2, free body diagram for M1. On M2, I have the external force F, and then there's a spring force here. Now the spring force, assuming that K2 is, X2 is greater than X1, that means the spring is in a stretch situation and the spring force goes to the left. And this spring force will be K times the deflection in the spring, which is the difference of the motion between X2 minus X1. This is the spring force. The damping force is C times the velocity, and the velocity is X2 dot minus the velocity of the mass 1 X1 dot. So it's basically the spring force, but the time derivative of the spring force and replacing the K by a C. Now, for M1, there's the spring force K1 times X1. That's the stretch in the first spring, and the damping force C1 times X1 dot. Now, there are a couple of more forces according to Newton's third law. For each action, there's a reaction equal magnitude, opposite in direction. So, opposite to this spring force, I'll have a spring force applied on mass 1 and a damping force applied on mass 2 in this direction, and both are equal in magnitude. Now, Newton's equation, we will have to have two of them for each mass. For mass 1, sum of forces is equal to M X1 double dot, and looking at mass 1, we have positive forces K X2 minus X1 plus positive C X2 dot minus X1 dot, negative force K1 X1, negative C1 X1 dot, and there are no forces, M1 X1 double dot. Now, this K is actually K2, this is C2, so this is K2, C2, and rearranging the equation, M1 X1 double dot plus C1 X1 dot and C2 X1 dot. So this is plus C2 all times X1 dot K1 X1. So this is K1, and there's also another K2 multiplying X1, so that becomes K1 plus K2 x1. And that's it for x1. And then we have minus, this goes to the other side, becomes minus c2 x2 dot, and this x2 goes to the other side, so minus k2 x2 equals 0. And this is the first equation of motion. The second equation of motion, this was for mass 1, so for mass 2, the second equation of motion is the sum of forces equals m2, this is m1, so m2 x2 double dot, and we have a negative k2 x2 minus x1, and we have negative c2 x2 dot minus x1 dot. We have positive f equals m2 x2 double dot, and rearranging I will get m2 x2 double dot, and then for the x1 dot term I will have minus c2 x1 dot, and I will have minus k2 x1, and then I will have plus c2 x2 dot, and a plus, this minus going to the other side becomes plus k2 x2 equals, and I will leave f on the same side, so equals f, and this is the second differential equation. So the second equation of motion of the system. So this is equation 1 and equation 2, 2 degrees of freedom system, 2 differential equations. The equations are coupled, which means that the independent variables exist in both equations at the same time in the two equations.